Right, Frank, thank you very much. It is a pleasure to be here. For those of you who don't know, I lead Ubuntu and lead product strategy at Canonical, the company behind Ubuntu. And Ubuntu is a platform that's very widely consumed in scale-out, large-scale, cloud-type environments. So this morning I wanted to dance a little bit with the demo gods and show you a little bit of some of the operational transformations that come along with some of the extraordinary physical infrastructure transformations that you're seeing described and discussed here at OCP. And I want to start with a simple question. How fast can you integrate profound change into your environment? And almost everything that's different between traditional IT and the next wave of the operations, the things that we've learned from the mega data center operators, boils down to that question. How fast can you integrate change into your environment? And so I want to start with something that is, that many would say is sort of impossible. The University of Texas in San Antonio has loaned us a lab of diverse hardware, all kinds of servers, some OCP, some not, some old, some new, and we're going to turn that into an OpenStack cloud. And here's how. So I'm going to have to make some choices. I'll have to choose a hypervisor technology, and I'll have to choose a software-defined network technology. Everything that I need there is pre-populated because the system essentially understands itself. And I have to choose some software-defined storage options for object and block storage, which I'll do. And then I have to allocate some hardware, and I'm just going to go ahead and say, use it all. And with a little bit of luck, that will transform those 70-odd servers into a OpenStack cloud. And when it's done, this is what you'll get. You'll get a dashboard showing that cloud and all of the automated management decisions that have been automatically made on your behalf to keep that cloud healthy and growing and to present to you the status of that cloud. Now, if you've ever tried to build an OpenStack, you'll know that that's pretty incredible. But what will really blow your mind is that all of the major software-defined network vendors, software-defined storage vendors, and hypervisor vendors have indicated that they would like to present their solutions in that framework as well. Now, I love OpenStack. The majority of the big production OpenStacks out there are on Ubuntu, and so we've learned a great deal about it. But I'm not showing that because I think everybody here should go out and build an OpenStack. I'm showing it because I think it illustrates the potential for radically accelerated operational efficiency. Now, Jay talked about efficiency in the engineering sense. There's also efficiency in the economic sense, and those two go tightly together. And if you think about your infrastructure today, there's the cost of the materials, and OCP is squarely aimed, in the very strictest sense, at the cost of materials, re-architecting materials for efficiency of energy, for efficiency of economics. But think also about your operations, what it takes to run that infrastructure. And I hear folks saying that sometimes that's twice, sometimes that's 8 times the cost of acquisition. We all know that hardware is a lean industry, so even squeezing all the margins out of that gives you only specific kinds of gains. But think about your operations and think about the potential efficiencies that can be created there if you move to the sort of automated processes that drive the mega data center operators. Now, to make that OpenStack vision happen, there are 2 key pieces of open source software. They're in fact general, they're not limited to OpenStack. And one of them is this, Metal as a Service, which we've built in collaboration with a number of OCP vendors. And MAAS, Metal as a Service, essentially guarantees complete automation of the physical layer in the data center. So it does inventory, it does commissioning, it does provisioning, operating system installation, and ultimately, as you retire hardware, it'll erase all of the data and decommission that hardware. So I want to show you a little bit what that looks like. So this is the Metal as a Service that's running in Texas. This is the environment that the autopilot is looking at to build that cloud. And you can see the diverse hardware that's in there. But over here, I have a little orange box. And this is actually a portable cluster. We built this to sort of show people OpenStack in their offices, but it's now being taken into deserts by geology teams because they love the idea of having a portable cluster. 10 little Intel microservers in there, and the lights indicate which ones are on. So let's go and take one. There's one here, node 3, and I don't know what's on it, so I'm just going to go and commission it. And that will get started. Nothing will touch the disk. The light just came on. Nothing will touch the disk, but in about 3 to 5 minutes, I'll know everything about that machine. I'll know all of the RAM, all of the serial numbers, all of the disks, all of the network interfaces, everything that you might want to know. But more importantly, MAAS lets us get machines on demand, metal on demand, in the same way that you think of VMs on demand from a cloud. And it does that with any operating system you like. So here, let's go and try that with, I'm a Linux guy, so I always find this kind of fun. Not that, well, that's a CentOS one. All right, let's do that. CentOS is not Ubuntu. And I'm going to install CentOS from scratch on one of those nodes. And then I'm going to install Windows from scratch on this one. It's been really fun to work in collaboration with Microsoft and a number of specialist agencies, cloud-based, who focus on the use of Windows in cloud environments to make all of this possible. So you should see over the next couple of minutes operating systems being installed from scratch completely remotely. Now, what MAAS really does is it abstracts all the differences between those different vendor protocols. This used to be really easy, IPMI and PXE, and most of you probably have scripts that you've created to drive IPMI and PXE to get stuff done. But in a hyperscale era, everything is changing incredibly quickly, and vendors are being forced, essentially, to innovate faster than standards can be set. And so all of these different chassis are coming out with different APIs, different protocols. And what MAAS does is abstract all of that away so that you can get a consistent experience across all different kinds of hardware. We have here those AMT-powered microservers, IPMI over here. We have the OCP Gen 2 chassis from Microsoft, which has a custom API, and yet all of those servers can be addressed through a common API. So that's really nice, but what are you going to do with it? So I'm very excited to announce that the wonderful guys at Chef have adopted MAAS, and they've produced two things, a Chef knife and a Chef provisioning library that will allow people who've adopted Chef to point their existing recipes at MAAS and deploy things on bare metal as easily as they currently deploy them on the cloud, which is pretty amazing. I think it's also important if you're going to abstract hardware, you need to do it in a general way. And so I'm very excited that MAAS has also been adopted by alternative architectures. So ARM servers can be powered by MAAS, inventoried, commissioned, operating systems installed, and so on, and Power servers as well, all abstracted through a common API. Also excited that the next version of MAAS will include, in collaboration with network specialists, a full open source IP address manager. So that means that MAAS will not only be able to enable and provision servers, but it will also track all the other devices on the network, and it'll track blocks of addresses that get allocated dynamically to services. The key idea here is that we're trying to take all of the manual steps that slow you down in your infrastructure and cost money to essentially will slow down your ability to absorb change effectively, and abstract that, automate that, make that effectively API-driven. You may have heard the term software-defined data center, and you probably have heard that from a number of different vendors as a complete solution stack. What I love about MAAS is that it's working across OCP and proprietary vendors. So that, for example, chassis like the HP Moonshot chassis is a hyperscale chassis with a custom set of protocols, and the C-Micro chassis from AMD and Cisco UCS, and these OCP chassis are completely abstracted using a common REST API with MAAS. So that's all open source, that's completely cross-vendor, supports all operating systems and models the network as well as the disks and all of the other physical assets in your infrastructure. So I think that really raises the bar for agility at the physical layer. The question then is, how do you go faster with your workloads? How do you go faster with your apps? So the second key piece of open source software that makes a profound difference here and enabled that OpenStack experience is something called Juju. And Juju is a universal modeling system for software workloads. So let me show you a little bit of what we can do with that. Say, for example, I wanted to deploy a lightweight content management system. Well, I'd need a database, and I would need a content management system, and I would need them to know about each other. And just doing that, if I'd connected that Juju environment to one of the MAAS clusters, would essentially now be spinning up physical servers, installing the relevant operating systems, installing the services, and configuring them, connecting them up to work in that environment. That's a live model, so if while it was building, if I wanted to extend it further, for example, I might say, okay, we're under load, so let's go and scale it out. You could go and say, I wanted another 3 of those. And you would have now 5 or 4 WordPress units, effectively, in that cluster. Now, this is a service model. If I switch to this view over here, you can actually see what's going on at a machine level. But in the modern era, we really just think about services. The next thing I think that is really important is that one can compose services from completely different vendors. There has to be no agreement, essentially, between those parts. They have to be independent, composable, reusable parts so that each individual team can go fast on their own. So a key idea here is that you want to keep those pieces encapsulated. MySQL doesn't know that it's being used with WordPress. It just knows that it's being used in a particular environment. To give that some teeth, over here we have the OCP chassis contributed by Microsoft. This is the Gen 2, I believe, OCP chassis from Microsoft. It's distinguished by being a 19-inch rack, so easy to adopt in traditional data center environments. Awesome equipment, has that custom API. And you can see in this MAAS interface that I'm displaying for that chassis, there are 4 nodes. 3 of them are powered up. 1 is providing that Juju interface, well, this Juju interface. And 2 are providing 2 workloads, 2 services. But I haven't integrated those services. What's interesting about this, though, is that in celebration of the fact that Microsoft and Canonical collaborated to enable this chassis for dynamic workload deployment across all platforms, I wanted to do something interesting with Windows. And in fact, one of those workloads is on Windows, deployed with Juju and with MAAS. The other is Linux. And so you can see how moving to a service-oriented architecture completely abstracts away the idea of the platform. We don't need to know or care what's providing that service or how it's provided. That's a vendor choice, effectively. What we care about is the integration. And so live, with running code, I want to go and ask those 2 pieces of software to start the process of integrating. So now this content management system on Windows is going to be told about this database on Linux, and that's all live. The other great thing about that is that this exact same experience is true on Azure. So you have complete coherence between the physical world on the Microsoft chassis and the cloud world on Azure as well. So the key story here is reuse across institutions. It's very expensive to do things very well. It's extremely expensive to hire the very best expert in, say, big data. It's also really expensive to hire the very best security guy, the very best performance guy, and the very best ARM or Intel or Power engineer. But with open source and with crowdsourcing, what we've learned is that if you can get reuse of a component across many different institutions, you can effectively, over time, get to the world's best execution or the world's best implementation. We know this from open source. Now we're bringing that to operations as well. So what can you do with it? Well, software-defined networks are a really important topic. And perhaps it's coming clear now how we can build that OpenStack cloud so efficiently, because OpenStack is a service-oriented architecture. And so this is OpenStack with a software-defined network from Metaswitch, one called Calico. This is OpenStack deployed with Juju using a software-defined network from Juniper. So this is Contrail. This is OpenStack deployed with the Alcatel-Lucent Nuage software-defined network. And this is OpenStack with the Open Daylight software-defined network controller. So again, breaking things down into services that are reused allows us to go much faster, it allows us to do much faster experimentation, it allows us to play, allows us to learn, it allows us to evaluate much faster. And we're working with telcos today to evaluate software-defined network options without PowerPoint slides, without presentations, just building OpenStack and evaluating, learning much faster, going much faster. But I feel equally strongly about software-defined storage. You know, I think we've seen a huge amount of innovation in the network. We're about to see another wave of innovation in storage, both at the object and block level, but also at the file system level. So that's why we're very excited to be working with a wide range of software-defined storage vendors, from EMC, Red Hat, and numerous others who are responsible for file systems, object, and block systems. And integrating all of those into OpenStack dynamically so that people can evaluate those solutions very efficiently. That service-oriented architecture also allows us to run the world's biggest OpenStack interop lab in Boston. There is OCP hardware there. There's also hardware from Quanta, IBM, HP, Dell, and Cavium, Applied Micro, any number of vendors. And that allows us to build with multiple permutations and combinations, dynamically, OpenStack, 3,000 times a month, generating a huge amount of data about what works and what doesn't work, what's efficient, what's not efficient. So again, being super efficient in reuse allows you to learn much more about your infrastructure, allows you to experiment. Off the back of that interop work, and based on tremendous customer interest in being able to stand up OpenStack clouds really efficiently, I'm delighted to announce that today, Quanta and Canonical are announcing a joint reference architecture for OpenStack. That's based on customer input and also an evaluation of the OCP roadmap. And there are 3 SKUs in that. One, to essentially allow you to stand up a lightweight OpenStack cloud. Another, to allow you to start to get a real sense of density and performance under your own workloads. And then a third, the full 21-inch OCP kit aimed at folks who are filling the data center for large amounts of bulk compute. And you can find details of that at ubuntu.com/QCT. Now, everything I said is general, and it applies just as much to other large, complex orchestrations that you might need to put together. So who's interested in big data? Well, turns out pretty much everybody who's interested in large OpenStack is also interested in big data. And big data turns out to be really quite hard. This is a Lambda architecture. It's kind of the cutting edge of data science. It's the synthesis of historical data, batch data, last month's receipts and last year's receipts, with real-time data. So what's happening right this minute in a Twitter stream or in a web stream. And that turns out to be really difficult unless you can model it with reusable parts. So this is what a Lambda architecture looks like with Cloudera solutions modeled in Juju. And this is what a different Lambda architecture looks like modeled in Juju with Hortonworks. There is a tremendous amount of reuse between those 2 environments. And the goal is to enable people to evaluate, to enable people to go fast, to enable people to experiment, to enable people to iterate, and to enable people to collaborate. Now, I wanted to touch on something that's very dear to developers' hearts right now, which is the subject of containers. You might have picked up that there's this huge shift or embracing of lightweight Linux containers over virtual machines. And most of that work is happening, I'm delighted to say, on Ubuntu, both on the cloud and on bare metal. And we're delighted to lead this shift away from traditional hypervisors towards what you might call a lighter visor in the form of the Linux container daemon, LXD. Now, LXD effectively has all the properties of a hypervisor. You create general machines, so you spin up CentOS, you spin up RHEL, you spin up Ubuntu. The machines look and act just like virtual machines, except you don't have the 20 to 30% overhead of virtualization. Now, they're only appropriate for certain environments, but they are an amazing disruption in density and in performance for people who want bare metal performance or people who are running many, many small workloads. So I would encourage you to look at LXD for that. And if you shrink a LXD container down to just a single process, just a single application, then you have something called Docker, which you might just have heard about recently. Docker is incredibly popular. It gives developers an amazingly powerful delivery mechanism for their code into production. I wanted to show you the fruits of some of our collaboration with Google. Oh, you know what? I missed an entire thing. Here, this is Ceph deployed on this stack velocity rack with OCP hardware. We deployed that just before the speech this morning. So that's Ceph running on there. And I just quickly want to go and add some more storage. So I'm going to go put another 3 units on there. And you should see some lights turning on and more Ceph being allocated. So bulk storage, bulk compute, dynamic allocation of machines to compute. So let's go and have a look at Docker. Now, Docker itself is just a key primitive. It just delivers one piece of code to one server. What's exploding is the number of ways to manage and control that. And so I wanted to show you this pretty cool thing from Google. This is something called Kubernetes. Kubernetes is a kind of management control system for Docker. And so simply by dragging and dropping this onto a Juju GUI, which I've hooked up either to the cloud, I could do this on Azure, I could do this on GCE, of course, I could do this on bare metal. I've created a working Kubernetes environment. And that Kubernetes environment essentially then offers a set of Docker services to your developers. We are in a time of profound reinvention and radical change, and your developers are absolutely going to love that. Now, everything I've spoken about so far has been for your elastic environments, clouds, large-scale environments where you have thousands of servers or hundreds of servers, and where servers can substitute for each other. There's one last thing that I want to touch on, and that is for the parts of your infrastructure which are the opposite of elastic. You could call them crystalline. So your switches, your routers. If you lose one server out of 1,000, the other 999 can help out. But if you lose a switch, you lose the rack. And so we feel that that kind of environment needs a different sort of platform. That's why we were so excited to announce and to launch something called Ubuntu Core, which is all the same software, the same kernels, the same libraries that developers are familiar with, just delivered in a format which is suitable for appliances. So you get transactional updates of the system plus transactional independent updates of applications. So you can roll back, gives you a very crystalline, precise view of all of that infrastructure. And the reason I tell that story is because last week it was the Mobile World Congress, and we had an amazingly cheap Intel x86 1U server, which had been set up as a switch. It had a bunch of network ports on it, and somebody had written a little app that essentially treated those ports as a switch. And we had that there as a sort of proof of concept, and telco and NEP type vendors were having a look and all very excited. That was Monday. Tuesday, somebody came along and said, here, try this. And in his hotel room, he'd created an app for that switch, which would stream monitoring data from that switch back to the Azure cloud. And Wednesday, a guy came along and he said, try this. Different guy. And it was an app which installed F5's line rate on that switch. And so I think the stories that Jay was telling about unlocking innovation in these traditionally closed environments, as switches and routers, are absolutely true. By providing developers with open platform that they can easily get access to, or that essentially looks to them like a standard virtual machine or a standard server, plus an open platform that they're familiar with, something like Ubuntu or another platform that they're familiar with, plus good mechanisms for the delivery, installation, update, management, and so on of applications, I think we're about to see another wave of transformation. OCP has already delivered that, I think, for core infrastructure, elastic infrastructure. And I believe it's going to deliver it for the Crystal infrastructure as well. Anyway, thank you very much. And thanks to the folks at OCP who lead this work. It's extraordinary. Thank you.